Hi everyone, and welcome to this lecture. This lecture I want to talk about the subspaces of vector spaces. Now, in my last lecture, I talked about vector spaces and how to prove that a set is a vector space. Remember, we went over the 10 axioms one by one to prove it that it was a vector space. Now, what is a subspace? A subspace, and you can call that W of V, which is a vector space, is a non-empty subset of the vectors of V such that U and V in W is in the subspace, and R being a real number or scalar, we can also have U plus V in W and R times U in W, closed under addition and closed under the scalar multiplication. So if these two work, then you don't have to prove all the 10 axioms, that these two are enough. One thing to be careful, that always zero vector has to be a member of the subspace W. So it has to contain the zero vector. Sometimes it's obvious, and sometimes if it's not, you can go ahead and as a third part of the proof, just to check to see if that contains the zero vector. Be patient, and with examples I'll show you. But going over that, why the proof of why the zero vector is a member of the subspace. So we said that W is a non-empty set. That means W has at least one member. So any scalar multiple of V must be in W. So that means C times V must be in W, or must be a member in the W. And if C equals to 0, because C can be any real number, is 0, so 0 times V is 0, the zero vector, so it is in W. So, and therefore I put zero vector is always a member of W. Now, little note here, for Rn, there are two trivial subspaces. One is the zero vector, zero subspace, and Rn, all Rn itself. Now, to prove subspaces, I want to refresh your memories of the important vector spaces we saw in the last lecture. One was R set of all real numbers, R2 set of all ordered pairs, R3 set of all ordered triples, and Rn set of all n tuples. So, and we had all the functions, continuous functions on the real number line. You see this, you can see that notation with a C, or you can see that notation with an F. I put both of them for you. Or C bracket AB, these are set of all continuous functions defined on a closed interval. Then we had set of all polynomials, set of all polynomials of degree less than or equal to n, together with the zero polynomial, set of all m by n matrices, and set of all m by n square matrices. For all these 10, the way you prove, you have to do the 10 axioms one by one and then see if they're satisfied. So for those, these are vector spaces. Now we can have subspaces of those, and we can see if it's a subspace or it's not a subspace. So let's start with this example. Determine whether x plus 2y equals to 0 is a subspace of R2. For a proof like this, there's several ways of doing it, but one way of doing it, part one, you can writing the set W. So we know that x plus 2y equals to 0 is the equation of the line passing through the origin. So what you can do is isolate y, and you get negative 1 over 2x. Y equals, so we know that's the slope, and the y-intercept in this case is 0 because it passes through the origin. So our subspace, let's first define it. So we have the xy component, and we know that's in R2. X is x, but y is negative 1 over 2x. X and y, they're both the variables are with real numbers. Now let's start the proof. That's part 2. You can write u to be x1 negative 1 over 2x1 and v x2 minus 1 over 2x2. And of course we have our scalar here, c the constant, which is a real number. Vector addition, u plus v is going to give us pretty straightforward x1 plus x2, that's the x component, and negative 1 over 2x1 plus x2, that's the y component. That's exactly what we have. If I put capital X for x1 plus x2, that's going to be also negative 1 over 2 times capital X. It looks exactly the same way as that. So that's why we say it's in W, so it's closed under vector addition. Scalar multiplication, c times u is going to give us cx1 negative 1 over 2 times cx2. Again, we can, if you call this x and that x, it's the same form. We get x and negative 1 over 2x, so that's also in W, and it's closed under scalar multiplication. I put a note. We can check for if you see if that contains the 0, 2, or that vector. If x equals to 0, y equals to 0, say yes, it does. So it does contain the 0 vector. So it is. It does contain. So it's for sure a subspace. Contains the 0 vector. W is a subset of R2. So it's important here to check this last part if you're not sure. Now I put another example. Here we have x plus 2y equals to 1. Is this a subset of R2? Question. Let's write the set. Isolate y. Again, you can say W is xy, and that's in R2. And x, you write x, but instead of y, you can write negative 1 over 2x plus 1/2. Isolate y. And x and y are real numbers, just the same way we did the first proof. Let's start the proof. You can call u x1 negative 1 over 2x1 plus 1/2, v x2 negative 1 over x2 plus 1/2, and c a real number. U plus v, if we add these two vectors, let me go here, you get x1 plus x2 negative 1 over 2 times x1 plus x2, and we get 1/2 plus 1/2. So, and if we add these two, we get 1, and we notice right away this is not closed under the vector addition. So you can stop right there and say if this is not, it's not a subspace. So also another way of proving this, if x equals to 0, then y is going to be 1/2. So we get 0, 1/2, so does not contain the 0 vector. So that's the reason that another way you can show it, that W is not a subspace of R2. So the only, actually we can go over this note. I put the theorem. The only subspaces of R2 are very important. Please remember that the 0 subspace, that's the 0 vector. So which is 0, 0. You can try, and both operations are going to both scale vector addition and scalar multiplication for 0, 0. Then the second one is the line through the origin, y equals to mx, which we just showed, and all are 2. So the set, if you write it all are 2, you can say the set u1, u2, and so on. So u1, u2, and all the vectors in R2. If you do that, it's going to work also. The only subspaces of R3. So we have the 0 subspace. Again, if you write that vector is going to be 0, 0, 0. So that's a subspace of R3. The line through the origin to the way you can show that, you can say x equals to at, y equals to bt, and z equals to cd. These are the parametric equations of a line. So write your vector and then try the two axioms, uh, addition and scalar multiplication. The planes through the origin, a plane through the origin in 3D or in R3 is written as ax plus by plus c is equals to 0. I will go over the proof of this. Please be patient. And of course, all R3. Now let's go over some examples. We want to have a couple of examples, the subset of continuous functions. So again, you write it like that, c from negative infinity to infinity, or I just put that notation if you see this. So it's the same thing. Is the set of all even functions f of x, f of negative x equals to f of x, a subset of continuous functions? So let's go over the proof. Part one, you can write the set. So W, we know that f of x is a continuous function such that f of negative x equals to f of x. So the way you can prove this one, we can say f of negative x is f of x and get another one, g of negative x equals to g of x. And of course, our constant or the scalar, which is a real number. Now, if I call h of x f of x plus g of x, that's f of g plus x, and I can write h of x equals to f of x plus g of x. That's the same thing as saying f of negative x plus g of negative x. That's f plus g of negative x, and that's h of negative x. So h of x equals to h of negative x. So it's h of x is also even. So we know it's closed under vector addition. C times f of x is c times f of negative x for both c being greater or equal to 0 or less than or equal to 0. Or you can just take it, doesn't make a difference. So it is closed under scalar multiplication. So conclusion, W is a subspace of all continuous functions. Note, if you want to take 0, if f of x equals to 0, also f of negative x equals to 0, so it does contain the 0 vector. Example 3, try to do another one for all continuous functions. Is the set of all positive functions f of x greater than 0 is a subset of all continuous functions. Let's write the set, just like examples before. So we have our f of x is a continuous function and such that f of x is always positive. Now let's start the proof. So, and can put that part 2. F of x is greater than 0 and g of x is greater than 0. So we pick two functions, just like before, and our constant, the scalar. We check f of x plus g of x is positive. If you had two positive functions, the result will be positive, so it's closed under vector addition. C times f of x is greater than 0 if c is positive. However, c times f of x will be less than or equal to 0 if c is less than or equal to 0. So this is not closed under scalar multiplication. Right away you can write the conclusion that it's not a subspace of all continuous functions. So here I'll call that, we can call V or W, it doesn't make any difference. That's why I wrote two different notations. Let's try this one. Set of all square matrices. Is the set of all square upper triangular matrices is a subset of set of all square matrices. So now Well, this is it for by providing the set, step number one. So you can say A and you can write is the matrix the compact form. So you know that's an m by n square matrix. And we define it such that it is an upper triangular matrix. That means Aij equals to 0 if I is greater than j, and Aij is not equal to 0 if I is less than or equal to j. Basically, upper triangle, I wrote that for you. So if I is less than j, then it's not 0. If I is greater than j, then it's 0. So now let's start the proof. We pick two upper triangular matrices. We can call them first one A, then second one A. C is A plus B. So if you add A plus B, you get an n by n matrix. It's also an upper triangular matrix. So that's in W. And I wrote that for you here. Again, Cij equal to 0 if I is greater than j, and Cij is not equal to 0 if I is less than or equal to 0. So it is closed under addition or vector addition. Scalar multiplication, if you take an upper triangular matrix and multiply it by C, you only multiply the lower triangle is going to be 0, and what you get another upper triangular matrix. So it is closed under scalar multiplication. So you can say W is a subset of square matrices, all square matrices. So all upper triangle matrices, they can be a subset of all square matrices. I put a note for you here. The zero matrix is both upper triangular and lower triangular, or and even diagonal. So you can say it contains the zero vector, and in this case, that's a choice. But always remember, I always put that in my proofs. Now the last example I did, so we went over this, but let's see how you can prove that. Again, we are in R3, the set of all order triples. So that's our vector space. Show that the set of planes passing through the origin, AX plus BY plus CZ, is a subset of R3. And I do want to go over this so you see how you can prove that. Same thing, you can write the set. So we are in R3 such that we have the equation of the plane. When you have AX plus BY plus CZ equals to 0, this is an equation of a plane passing through the origin. We are going to see this in our next lecture also. So in this case, it's very good to choose parameters. It's going to make your job very easy. So I did z equals t and y equals to x. So x plus cy plus z, you can write that at ax plus bs plus ct equals to 0. Isolate x and you get that. Negative b over as minus c over at. So w is in R3. That's x right here. And we said y is s and z is t. And a, b, and c, they're all real numbers. Let's start the proof. So we can call u, which we write it s1 t1, and v, which we write it with s2 t2. And here I called alpha because we had a, b, c, so alpha is our constant. Same thing, u plus v, you add the components. And if you do that, the result is going to be negative b over a s1 plus s2 and c over a t1 plus t2, s1 plus s2 and t1 plus t2. If I call s1 plus s2 s and t1 plus t2 t or capital S, then we get the same form, negative b over as minus c over s, a, t, s, and t, which looks exactly like this. So we can say it's in W, so it's closed under addition or vector addition. alpha times u, that's pretty straightforward. You take alpha and multiply it by u, and what you get, negative b times alpha over a s1, negative c times alpha over a t1, and alpha times s1 and alpha times t1. And this is the same format we have here. So these are just constants. So therefore, it's closed, it's in W and it's closed under scalar multiplication. Always, if you want to put that note, it's good to do it. If t is 0 and s 0, then we get all three components to be 0. So contains 0, 3. So W is a subspace of R3. So just to summarize, this proves what you can do best. One way of doing is write the set. So please watch this video a couple of times, how you can write the set, how you can have your components, and then once you have all that, pick two vectors, do the vector addition, and it has to be in W, and do the scalar multiplication. It has to be in W, and it's a very good idea to check if it contains the zero vector. I think that's good enough for this lecture. Again, please watch it a couple of times, 2 or 3 times, and try some problems on your own. Thank you and have a great day, everyone. I'll see you in my next lecture.